stations, and she was the founder of this network. Then from 1991 to 2016, she was professor of geophysics at the University of California at Berkeley and director of the Berkeley Seismological Laboratory. And since 2016, she's professor of the graduate school at the UC California, Berkeley, and honorary professor at the Collège de France. To her research, there is a very nice quote that I found about her research, just to tell you a little bit of glimpse of what she's doing. So Professor Romanowicz research is characterized by innovative seismological theory, sophisticated numerical methods, and insightful interpretations that have illuminated key Earth processes. So I just took this from many of these quotes that we have from her research. So she has, in fact, a broad spectrum ranging from Earth and planetary science, deep Earth structure and dynamics, earthquake processes and scaling laws, real-time estimation of earthquake parameters, development of modern broadband seismic and geophysical observatories, etc., etc. And for her really seminal work, she has received a lot of awards and honors. Let me just mention some of them, but there is a long list. So in 2020, she received the Wollaston Medal of the Geophysical Society of London. In 2019, she received the William Bowie Medal of the American Geophysical Union for her outstanding contributions for fundamental geophysics. And this, I found this very, very nice, and for unselfish cooperation in research. I haven't seen that so often. She also is received for instance, in 2008, the Chevalier de la Légion d'honneur. I think this is the highest French Order of Merit, as far as I know. She also has received the Alfred Wegener Medal of the European Union of Geosciences, and many, many other awards and honors. We're very happy to have you here, that you have some time to tell us about your research and about your life. And Professor Romanowicz is going to talk about imaging the Earth's deep interior using seismic waves. So the stage and the floor and the screen is yours.
Thank you very much, Rosa, for this very detailed presentation, and nice to meet you.
Nice to meet you.
Yes, and also thanks to the organizers to give me this opportunity to tell everyone around about my field. So I'm going to try and share my screen. It might take a few steps because of some problems with my computer. So I'm okay.
Yes, we see your screen.
Okay, so I just have to swap displays. If I can find my, sorry about this. Okay. And now once more. Oh gosh. My computer is slow. Okay, does this work?
Yes, now it works. We see your first slide. Yeah, very good.
Okay, so let me then start. So I'm kind of happy to be following up on Margaret's talk, because even though we're talking about very different kind of matter, we're back now to condensed matter, but we're also going to talk about elasticity. So our field is quite recent. This is a very nice representation of a picture by Athanasius Kircher from the 17th century, which sort of depicts what we thought until relatively recently was causing all the natural disturbances on the Earth, such as volcanoes, volcanic eruptions, and earthquakes. Basically, there were cavities full of boiling materials and fires inside the Earth. Today, we know much better, and that's thanks first to Alfred Wegener, who in about a century ago realized that there were affinities in the shapes of continents between Africa and the Americas. And there were also affinities in the geological formations and in the fauna and the flora, and proposed that continents drift. Now, it took quite a while for this theory to be accepted because people couldn't figure out why the continents would move. And you had to wait until the development of fluid mechanics in the 1930s to understand that, in fact, the interior of the Earth is dynamic and it is basically releasing heat. And from that, there are convection currents inside the Earth's mantle, which serve to basically get rid of the heat, just like you would have in a fluid heated from below, on which you put a cork at the surface, and the convective currents would cause the cork to wobble. Of course, in the Earth, the situation is somewhat different. The geometry is different. We have a rocky mantle, a fluid core, already yesterday, Irina introduced very well the concept of plate tectonics. We have about 20 tectonic plates on top of the mantle that are being moved by the convection in the mantle. So what we're interested in is really understanding what is really going on. What is the platform of this convection? How the plates are coupled to the underlying very slow motions, because these motions, now we're talking about motions of centimeters per year, which is the motions of the plates, or slower. And just to give you an idea of why we're interested in this is there's two ways the Earth is extracting, we're extracting heat from the Earth. One is the primordial heat that was from the origins, from when the Earth was formed, as is still being sort of released. And then there is also heat production that continues from radioactive elements that are trapped in the Earth's crust and the mantle, and possibly some in the core. And depending on the balance between these different sorts of heat release, we may have very different types of planforms. If the fluid is heated from below, we expect to see mantle plumes, like you see here in an experimental setup. If what is prevailing is the internal heating from radioactive decay, then we would see very narrow downwellings and very diffuse upwellings. And also maybe, or very likely, the circulation in the Earth's mantle is not only thermal, but also is influenced by chemical heterogeneity, the compositional heterogeneity. Now, we can't go inside the Earth. The deepest hole is only about 12 kilometers deep in the Kola Peninsula in Russia and Siberia. And the Earth's radius is 6,400 kilometers. So this is just a very small sort of glimpse into the interior of the Earth. And in fact, all we do in geophysics is really remote sensing. And in order to understand the Earth's interior structure, its dynamics, its evolution, we need to combine information which is partial, information from different fields, which involve chemistry, mineral physics, the properties of deformation of materials, the rheology, seismology, which I'm going to be concentrating on, and then also geochemistry and cosmochemistry, and other fields like geomagnetism and geodynamics, which provide a sort of a synthetic way to model or to synthesize motions. Now, seismology is my field. I use seismological tools to investigate the Earth's internal structure to try and understand its dynamics or contribute to understanding its dynamics. It's quite this part of seismology, which is called global seismology, is quite recent. It really dates back to an observation by von Reuber-Paschwitz in 1889. He was with some colleagues looking at, he was interested in tides, in Earth's tides, the solid tides of the Earth. The Earth has, of course, ocean tides, but the moon and the sun are also attracting the solid part of the Earth. And with very sensitive tilt meters, you can analyze and follow these tides. But on a particular day in April of 1889, he noticed or he observed a disturbance which was very much shorter than the disturbance due to tides. It lasted maybe an hour in Potsdam, this observation in Potsdam. And what was special about it is that it couldn't have been like a cow hitting the instrument, because it was observed simultaneously in another observatory a couple hundred of kilometers away in Wilhelmshaven. And several months later, he read in a report in Nature. Of course, there was no internet, no telephone, etc. And he was reading a report that there had been an earthquake on that day at about that same time in Japan. And he basically understood that what he was seeing was the earthquake waves, the waves generated by the earthquake, the seismic waves that traverse the Earth between Japan and Germany. So that's how the field was born. Today, we know much better. Of course, and I don't know if I'm going to be able to run this movie, yes, here it is. Oops. We know how the waves propagate inside the Earth from a source to a, yeah, I'm sorry, it's not going to work. Oh gosh, yes. We have different types of seismic waves, and the wave field propagates inside the Earth and interacts with the different layers, with the different discontinuities in the Earth, the major one being, of course, the surface of the Earth, and then the limit between the solid mantle and the liquid core. And a simple way of following these waves is through so-called ray theory, where you can sort of map the path of these waves in a sort of infinite frequency kind of approximation through the Earth, and see which ones were reflected on the surface of the Earth, which is this example, and others will have followed other paths. And if you then record these disturbances in an observatory on a seismometer, on a very sensitive instrument, you have a sort of succession of waves that arrive, which you can identify after many years, decades of accumulated knowledge. We can identify which wave has gone through which part of the Earth, at least for the main ones. And if you align records that have been obtained at different distances from a source to the station, and we measure these distances in terms of angle from sort of distance, arc distance measured from the center of the Earth, you can see the move out of these waves, which arrive later and later for larger and larger distances. The seismic wave is quite rich. First of all, of course, the waves traverse the Earth and refract and reflect, and they also convert. We have two types of waves, compressional and shear waves. These are elastic waves, and they are also can be polarized in different ways. And from that, in addition to what we can get from a sort of standard record, which maybe will last an hour, we have another type of observation, which is for a long times. Now we're talking about tens of hours or days, where waves, surface waves that whose energy is concentrated near the surface of the Earth, circulate from the source to the receiver and go round and round the Earth in different directions many times. And each time the energy goes through the station, you will see an arrival of energy like this, and it decays as a function of time because the Earth is not completely elastic. It loses. There are processes that that cause loss of energy as a function of time and distance. But if you take the spectrum, so if you go into the frequency domain of this type of long record, you actually, what you see are peaks of at very, very specific frequencies. And here we are in the range of 0.3 millihertz, which is the gravest normal mode of the Earth. We're seeing the peaks of the free oscillations of the Earth from 0.3 millihertz to 1 millihertz here, but you see them at shorter frequencies as well. And each of these peaks has a characteristic shape. For example, this peak 0S0, they have a nomenclature, is the so-called breathing mode. The Earth expands and contracts. The other peak here, the other mode here is the football mode, where the Earth is contracting in one direction and then in another direction, etc. What's important is that each of these peaks has some specific sensitivity to the Earth's internal structure, and it is sensitive to different parameters, the shear velocity, the compression velocity, and the density. So by analyzing the frequencies of these peaks, we can have some idea of the internal structure of the Earth as a function of depth. Very much like we can, if we listen to a bell, the sound of the bell depends on the shape, on what it's made of, and its size. So in the 1980s, by the time of the 1980s, we had a pretty good idea of the internal structure of the Earth in what we say 1D. The Earth is to very good first approximation spherically symmetric, which is very convenient. And thanks to the measurements of the normal mode frequencies and some travel times of waves inside the Earth, of other waves, we had, by the time of this model, which was called the preliminary Earth model, but it is already, even today, it is used as a very good 1D reference. And we see the variations with depth of the elastic parameters, and we can then relate them to the composition of the Earth that is given to us by different disciplines, primarily mineral physics, the study of rocks under compression at high temperatures and pressures that are inside the Earth, from which we can then derive a knowledge of more or less what the internal constitution of the Earth is made of. Note here in the mantle, right? So the core is the external core is fluid. There is no shear velocity is zero. No shear waves propagate directly inside the core. Those that do have to convert to compressional waves and then convert again to shear waves as they go through the inner core of the Earth, which is solid. And Irina told you about the discovery of the inner core yesterday. In the upper mantle, we have discontinuities of structures that can be associated with changes in the crystalline structure of the main constituent of the upper mantle, the mineral olivine. As the pressure and temperature increases in the Earth, there are several of these changes in the crystalline structure. The major discontinuities, which correspond to these phase changes that are at these 400 and 660 kilometers depth, and there's another one at 520. And then at the base of the mantle, there is also a region which we call the double prime layer, which is known for its peculiar properties and a lot of heterogeneity, as you see here. So a lot of departures from this 1D structure. Of course, the Earth is not rigid. the plates are rigid, but inside the mantle flows at long time scales, and that is described to first order by a viscosity structure as a function of depth, which can be obtained from the analysis of the gravity field of the Earth, and also the rebound of continents that are losing their glaciers. And the viscosity increases with depth in the Earth. On average, it's about 10 to the 21, between 21 and 22 Pascal seconds. So now what we're really interested is in the dynamics. And to get the dynamics, we have to look at the departures from the 1D structure, which is really a very static view of the Earth. And there, the tools that have been developed, in fact, since the 1970s, are seismic tomography. So seismic tomography is similar to medical imagery. Basically, you send waves. It's non-invasive investigation. You send waves from sources on the borders of the body, and you record them also on the borders of the body in with appropriate sensors. In seismic tomography, we have what we're measuring is basically the propagation of seismic waves. We measure primarily their travel times, but sometimes also their amplitudes. And as they go through different types of materials and different temperatures, they will be slowed down or sped up. And to first order, when a wave is slowed down, it generally means it's going through a hotter than average material, and when it's faster than average, it goes through a colder than average material. The principle of tomography is really that you need to have illumination from many different sides of the body in order to be able to determine, localize some heterogeneity, some anomaly, and also determine its shape and its strength. And this is a simple example showing that if you have only observations in one direction, you will not be able to localize fully the anomaly. You need observations in the other direction. In the Earth, of course, the waves travel through curved paths. And what we have is really an inverse problem. I'm not going to go into details, but very quickly, we have data which are our travel times or waveforms, which are related to a model of the Earth through physics, right? And it is usually a nonlinear relation. And we distinguish the forward problem, which is we have a model, we know the physics, we will get the data, but what we're really doing most of the time, and the interesting part is how do we get from the data back to the model? So it's an inversion, except that even if you linearize, generally the matrices are non-invertible, so you have to have a whole panoply of tools to be able to solve this problem. So as I said, the classical approach is the travel time tomography, and it is easily linearized. The problem we have compared to medical tomography is that our sources are natural earthquakes that are not distributed uniformly around the Earth. They are distributed primarily on the borders of the tectonic plates, as you can see here, and most of them are shallow in the first 30 kilometers of the Earth, although in regions where plate goes back down into the mantle, so-called subduction zones, they can reach up to about 700 kilometers depth. And also the distribution of our sensors is not uniform because the Earth is covered to the 2/3 by oceans, so that we have a concentration of seismic stations on continents, but going into the oceans is still a challenge. There are few islands, and even in the islands, the records are generally very noisy because of environmental background noise. However, I just want to point out that in the last 40 years, a lot of progress has been made thanks to progress in instrumentation, the construction of very broadband seismometers that can capture the whole frequency range that is useful for so-called teleseismic studies, that is a study recording and the band is from about 10 hertz to a few hundred seconds, up to the normal mode frequencies of the lowest frequency of 0.3 hertz. And we like to put our instruments in, isolate them in very deep vaults if we can, to isolate them from environmental and human noise. So very quickly, so the first models that were built in the at the end of the 1970s. Here is an image that was made later. I show this image because in 1977 there was no color to make images, but a few years later color appeared. And this is a first investigation of teleseismic P waves, so compressional waves, traveling at long distances and sampling all of the mantle. So the P wave is the wave that goes straight from a source through to a receiver along this type of path. And what was found then was something very fascinating, is that at the base of the mantle, we are here 400 kilometers above the core mantle boundary. And this is a map of the lateral variations in the P wave velocity, relative variations to the mean, to the average at that depth. And you can see a ring of fast velocities that is surrounding two regions of low velocity. And what was fascinating is that this correlated with the observed geoid. The geoid is basically the gravity field of the Earth that at a very long wavelength, with the high and it's expressed in height. So if the gravity is stronger, you will see blue colors. Gravity is lower, you'll see red colors. And this is quite unexpected, because you would expect that if you have a hot region, then the density would be lower and you would see a lower gravity, therefore lower geoid height. And you see exactly the opposite. And this, so you have a correlation coefficient which is negative. And these authors propose that this is due to the fact that there are lateral variations in composition, and that part of these lateral variations could be due to the subducted slabs, so the slabs of the tectonic slabs falling into the mantle all the way down at the bottom to the bottom of the mantle, and these slabs have a different composition. Or it could also be due to the dynamics inside the Earth, due to the convection, which causes surfaces of discontinuities to be deformed. For example, if you have an upwelling, it will push the Earth's surface towards the exterior, and therefore cause higher gravity. And indeed, these two ideas, which were first proposed at this time, are still the subject of many debates. However, these modeling has led to many interesting results. For example, being able to follow the subducted slabs, which you can see here in blue, as a function of time inside, basically interpret what you see deep in the mantle in terms of the time it took the subducted slabs to basically slowly move down into the mantle, which happens at the scale of millimeters per year. And for example, you can identify some very old slabs in here in the so-called parallel slab in North America, or the Aegean slab, which resulted from the closing of the so-called Tethys Sea almost 200 million years ago. I can't go into the details, but just to mention that this is quite fascinating, because other geophysicists, tectonophysicists, use paleomagnetic data to reconstruct the motions of the continents as a function of geological time, but they have a problem, which is that they can determine the latitude, the paleolatitude of the continents, but they have trouble determining the longitude. And being able to associate the subducted slabs in the mantle with these older positions of the continents basically gives you allows you to basically align the longitudes. Now, in the upper mantle, also the first models were very exciting, because here now we're looking at a model of shear waves, which was determined from the study of travel times of surface waves at a depth of 100 kilometers below the Earth's surface. And what you see is a very characteristic pattern, which reminds you of the ages of the ocean floor, as Irina yesterday explained. When new crust is formed, the plates then kind of move away from the mid-ocean ridges and age. And you can see very clearly, now this is another representation of a more recent model where you see more details, but essentially already in 1984, the main points were there, where you see the system of ridges, here the East Pacific Rise, where new crust is formed. You see the subducted zones where the plates goes back into the mantle and pushes out some of the lava, creating molt, or material which melts and creates volcanism, so hot regions. Then you also see in blue, so cold, fast, cold root cores of the very old continents. And when the picture was shown, it was both basically a proof that tomography works, because it basically reflects plate tectonics, but you could turn it around and say, well, it was also a confirmation of the validity of the plate tectonics theory. There are other things that you can do with seismic waves. There is anisotropy. Waves travel in different directions at different speeds, and that reflects the orientations at the microscopic plate of the olivine crystal in upper mantle, the olivine being the main component of the upper mantle. And you can relate those directions of the fast axis that you get from seismology, so from the macroscopic scale, to either fossil plate directions. So at a depth of 50 kilometers, you are very often observing, like in the Pacific here, the direction of plate motions that occurred 100 million years ago, or current plate motions if you go deeper into the convecting mantle. Now we have a better picture. How am I doing?
So we have now about 3 minutes to 5.
Okay. Okay, so I will try to move a little bit faster. We have a pretty good idea of the large scale, large wavelength structure of the Earth's interior. As we go deeper into the mantle, the structure changes. We lose the signature of the tectonics. And most interestingly, I will skip the rest. What we see here is subducted slabs, subduction zones, but I won't go into the details. But we see this very long wavelengths, very characteristic structure, which has been coined the large low shear velocity provinces, with this fast velocity ring, which we call the graveyard of slabs. And this is really interesting because if you take if you just take the longest wavelengths of the structure and you present it in a 3D kind of rendering, the fast ring of fast velocities goes through the Earth's rotation axis, and it is basically reflects. It also contains the pole of paleopoles of rotation of the Earth, and reflects some equilibrium in the sense of the basically of the rotation of the Earth, of the moments of inertia. And it is also what you would expect from a simple convective system of the so-called degree 2 convective in the system in the sphere, where you have 2 downwellings, 2 upwellings, and a ring of downwelling. And so today we want to learn more about the details, and we have all these questions about whether the large shear velocity provinces are compact, stable piles, are they domes that are oscillating, or are they simply a collection of plumes? And I really won't have time to tell you much about that, but we are fascinated by plumes because we have these hotspot volcanoes in the middle of plates, which cannot be explained by plate tectonics. You have a progression, age progression of extinct volcanoes, and which have been proposed to be due to plumes of hot material anchored at the base of the mantle and the plate moving over it. There are other reasons to think that the volcanoes, that we have these plumes, but to image them is difficult because if they are hot, they will be low velocity, and low velocity regions will be sort of hidden behind for waves. The most direct wave will go around the low velocity anomaly, and so you have to dig deep into the waveform to see it. And so in recent years, basically methodologies have been developed to look at the whole waveforms rather than just the travel times of main phases. And again, I need to basically conclude, but the field has been transformed in the last 10 years, 10, 15 years by the advent of numerical computations that, or basically the advent of high performance computing, which allow us to compute, to predict the seismic wave field in an arbitrary model of the Earth, using basically integrating the the equation of motion, the wave equation, numerically. And the method of choice is a spectral element method. And just to finish, I will just show some images from some of our work that now has really shown that mantle plumes exist. They are anchored at the base of the mantle, but they have shapes and that are very different from what you would expect in a purely thermal model. And so we need to work more on getting higher resolution and to understand better how these plumes, basically what they're made of, how they work, what rheology they correspond to, and how they interact with the and I have to click many, many slides to just show you sort of a cartoon which represents our, and I'll finish here, our current view of the mantle with some different processes going on in the lower part of the mantle, which is very sluggish, and a more vigorous convection in the upper mantle. And thank you very much. I'm very sorry for having taken so long.
Oh, no problem. Thank you very much. This has been a wonderful talk, and we got now a really dig into this world of the seismic waves. So let me see if there are questions. Please just post it in the Q&A. Okay, Falco, you have a question?
Yes, thank you. I was wondering whether the measurements of the Earth's magnetic field are at all relevant for determining the kind of questions you're answering, the kind of questions you're asking, but it's also related to the convection, right? But I'm not sure that that's really helping in any way.
So actually, the magnetic field, the geomagnetic field, the magnetic field of the Earth is used very, very much so, but not for the study of the mantle, but for the study of the Earth's core, or the study of the Earth's liquid core, where motions are much faster, 20 kilometers per year compared to a few centimeters per year. And in fact, we have a geomagnetic field as a result of the motions, of the convective motions inside the outer core, which basically by the principles of induction, right? So we have a dynamo inside the outer core. So the geomagnetic field is primarily used for that purpose. There are magnetic anomalies, of course, at the surface. In fact, that was a critical piece of information, where the magnetic anomalies recorded on the ocean floor for the basically the development of the theory of plate tectonics. But these are related just to the very top. They are magnetic anomalies that have been caused by hot material going through the Curie point and adopting the direction of the magnetic field at the time. Yes.
And maybe if I could add just one more short question, is these plumes that you mentioned at the very end, what's the stability, or what timescales are they stable here?
That is a very good question. That is an open question. We don't know. No, we have some evidence that they may have been stable for at least 2 to 3 million years, which is still a very small time with respect to the 4.6 billion years of the Earth. But they may have been stable longer. They are stabilized most likely by the fact that there is some density, some higher density at the roots. I didn't have time to talk about it, but this is some of the recent work that shows that basically suggests that there are regions of higher density right at the core mantle boundary, maybe an interaction between the core, which is denser, right? It's made of iron, and the rocky mantle. But that's how much we know so far.
Thank you.
We also have a question by Laura.
Yeah, first of all, thank you very much for this super exciting talk. I was wondering about the waveforms that you discussed. Is it currently more a challenge to build theoretical models, predict the waveform, and then compare to measurements, or are there also large uncertainties when measuring the waves?
So actually, you have, of course, to deal with the measurement noise. Actually, background noise at the sensors, because they're very, very sensitive. That is why we like to put them as far away as possible from the surface of the Earth, because there are disturbances due to the wind, to temperature, and at somewhat higher frequencies, just people, right, and vehicles, etc. But if you have a good record, there is the measurement of the waveform itself is pretty accurate, right? So yes, there are some uncertainties, but we have many more uncertainties related to actually the approximations that we have to make about the structure of the Earth, because it's an elastic structure. There are 21 independent elastic constants that you could be solving for. We have to approximate that. And then we also have, it's not completely elastic, it's inelastic. So we have to take into account attenuation factors and that sort of thing. So yes, many things to worry about.
Oh, wow, yeah, cool. Like really a theoretical challenge. Wow, thank you.
There is also a question by Tamara.
Yes, hi, thank you for your very nice talk. I wanted to ask whether, because you showed that you can, for example, extract the density profile of the Earth structure from seismic waves, but can you, for example, also draw conclusions about the composition if you assume or make several experiments assuming, okay, this and this material is inside of this, well, inside of the Earth at some level, and then you can maybe reduce the pressure in the lab and see how the density evolves. So basically the question is, can you draw conclusions about the composition from seismic waves?
Yes, so exactly. We have to work hand in hand with the so-called high pressure physicists, right? We call them mineral physicists, who take rocks. We have some good knowledge about the rocks of the upper mantle from what we basically collect at the surface. We have some knowledge about the composition from meteorites, right? From looking at meteorites and the composition of the solar system, etc. But with all these boundary conditions, we do make experiments. Or my colleagues who work in mineral physics do experiments in the lab where they take the minerals of the upper mantle, which are the most accessible, and make them go to very high pressures and temperatures to see what happens to them. And that's how they see the phase changes in the mineral structure. And then also at 660 kilometers depth, we see a decomposition of the upper mantle of the olivine system into oxides and perovskites, etc. And at the base of the mantle, there is a transition to a post-perovskite state. So we know the crystalline structure, and we have a pretty good idea from the experiments, but also now more recently from theoretical experiments, right? From ab initio experiments on mineral composition.
Thanks so much.
Thank you very much. I have one more question. So there is a lot of data being collected from all these measurements. And my question is whether for the modeling, you are also using machine learning type of approaches or artificial intelligence type of approaches, or this is not here very useful?
So yes, it is starting. We are using, for example, Monte Carlo methods to study simple problems. For example, like a layered structure in the upper mantle, where the parameters would be the thickness of the layers and the elastic parameters in these layers in 1D, right? And that is already a big problem. And that can be solved with Monte Carlo Markov chain kind of approaches, and is done. But if you want to model the 3D structure with the, very precisely, the numerical integration of the equation of motion is very numerically intense. I mean, it takes 4 hours on a supercomputer to compute one wave field across the Earth. So this is still not quite reachable, but there are, there are researchers that are trying to see how to, make use of artificial intelligence, and so someday we'll get there. But right now it's just too many parameters.
I see. Okay, so thank you very much for